Hey, how you doing? We are delving into linked lists. And we're going to start with a very simplified form of the linked list called what I call a poor man's linked list. It's kind of like with all the kerfuffles, all the poofy, nonsense out of it and direct and straight to the point, or to the code that actually makes a linked list possible. And so that's where we're going to start is with that, and then we'll go into hey, what does a linked list managing library look like, and then how does that all come together with this term that I'm going to use that's alien to Java, which is kind of funny because it's really not. I'm going to use a term today called a pointer. And the interesting thing about Java and C Sharp, those two languages are pretty much the same. Well, when I'm saying the same, I'm being very loose, but they got the same type of architecture. And what yeah, I'm already getting lost myself when we just started talking about linked lists. So typical. Yeah, totally lost me there for a second. We're going to begin with just the simple parts of it, and then move on into the implementation of it. And the pointer is how the mechanics of a linked list works. And the reason why those two languages are very similar, C Sharp, Java, is because everything in it, every data type that's created in those languages, and I call them my super languages, is a pointer. They're all pointers. And the way the language has been built, that has been taken out of what you have to be concerned with as a programmer. Because with these, specifically those two languages, you're dealing with a lot of what we call managed code. Python's sort of kind of the same thing. It's a more pure version of scripting. Java and C Sharp are, I don't want to get into that term. I almost want to say they're scripts, but they're not, because they actually compile to something a little bit more concrete. But pointers, yeah, we're gonna have fun with that today. Without further ado, let's begin. We are going to start with just a simple, we're only going to work with a simple Java with Ant application. And I'm going to call this linked list. Now I'm going to continue this on into the next video, which is going to talk about a linked list manager, but that's a good start. Project name, linked list. And we're using Java, and it looks like, no, I don't like that for a main class. Linked list. Good night. The hell with it. Maybe let's call it J linked list. For Java linked list. And by the way, guys, the best way of working with linked lists in both C Sharp and Java is to use the already built linked list. However, we want you to have a little bit more exposure to how that data structure, what we call a self-referential data structure, works, especially since the next extension of it is what we call binary trees, which is essentially what allowed Google to take over the world when they started working with data storage and binary trees. It's that kind of self-referential data structure or object that allows that type of memory to happen. And the reason for a linked list is because with arrays, the problem with arrays is no matter what kind of array you're dealing with, once you've allocated a contiguous block of bytes that we call an array, to increase its size from its initial instantiation, we have to create a whole nother array, copy the old array into the new array that's a little bit bigger. Yeah. So that means that if you have a million items, and with a lot of arrays, and especially in managed code like Java and C#, if you use up an array's space, it'll automatically double it for you. And then you use up its space again, it doubles the size again, but it still has to go through that process of creating memory that's twice the size or a little bit larger than what you have, and then copy all the data over to it. So it's not, arrays aren't the best solution when it comes to memory that's streaming or something that's receiving a stream. And kind of the idea is, well, what if I just want one more? What if I just want one more integer? I only have 100, but what if I just want one more? Well, you have to make 101 integers and then copy the old 100 integers into the new 101 integers, and then you could have one more. No. So what we've come up with is this self-referential type of memory management and what we call a linked list, where you are able to always just add one more without that intensive memory hole of always having to create new memory just to get one more item. And so that's why we use linked list is for streaming, for whenever we're just standing by and we do not know how many we need. Now, if we were reading a book, we could create a program that would go in and look at the page numbers in the book and know that it needs to create 500 pages of memory to hold that book. But what if it's just sitting there waiting for the next byte or waiting for the next 100 bytes? And it's only getting that data a little bit at a time. That's where you need dynamic memory that is not contiguous, not in array blocks, not in contiguous blocks that are set in size and range, which is what arrays limitations are. And so that we can say, hey, I just want one more, and we can build these apps that will keep listening on a port or be looking for a new file or anything where they can just add to the amount of items that are already on our container class, that our storage mechanism, which in lieu of an array, we use a linked list. And a linked list allows that behavior. And that's the reason for it. So what does that look like? Well, self-referential code means that you're going to kind of have some kind of form of recursion. Now, I mean, don't quote me on that too much, but it's sort of like that. But it's not where functions are calling themselves, but it's where objects are referencing more instantiations of itself. That's a mouthful. Yeah. But we're going to get our little handy dandy whiteboard out and we're going to mark up some things. But before we do, let's kind of get some action going here. Let's write some code. And what I'm going to want is I'm going to be talking about what we call a node class. Now, the node class is what is self-referential. And what I'm going to do here is I'm going to say new, and I'm just going to create a Java class that I call node. And why node? Why do we use the word node? Because it's unexpected. It's like doing a for loop with I and j. It's a standard way of naming a self-referential class so that we understand what it is. We just have to call it node, and everybody that looks at it knows, oh, that's a node that for data that's chained together in a linked list. So how do we actually make those chains happen? And how does it represent recursion? And it's really kind of a simplistic idea. And by the way, we're not going to be doing our linked list. I don't think there's no reason for templates. I think C# finally gave up and said, oh, fine, here you go. You can have your templates. Because you actually don't need templates whatsoever in Java or C#. Because everything is an object. So you just package it up, you box it up as data. So we can create a data class that is going to be just what we call an object. And then we can use dynamic binding to have it manage itself within that self-referencing behavior. So that means, well, what's the whole purpose for a node? A node is to store information and store where the next information block is at in memory. So that means that we need to use loosely a self-referencing pointer. And it's going to look like recursion, because what I'm going to do is every time that I create a node, I'm going to have some kind of data that I'm storing. And I'm being loose with my syntax right now. And I'm going to need another node that is the next position. It's the next node that's going to hold data. And this is where the self-referential part comes in. Because if we're in main, let's bring this together, because this is pretty much a node. This is what a linked list is right here. This is the very root of what a linked list is these two items right here. How does this node next work when we initially create a node? Well, in main, what we're going to want is we're going to want to instantiate node. And I'm going to call this the main node. I better not be using a keyword. Not the main node. Let's call it the root node. The root. Node root, that's not a very good root. En root, that's even better, okay. Equals new node. Okay. What does that do? All right, well, it says I want a node and to create a node. And then inside of here, we say node next. But to actually create a node in C# and Java, especially because everything's an object, we have to use the equals new statement to actually instantiate it, because we are working with pointers, and when we say equals new, we're saying, hey, operating system, give me the memory for this data type, and then we assign the pointer to the first block of memory of where that data starts in RAM. And so that's all implicit, when you use that new function. All the behind scenes stuff working with a pointer happens automatically. You don't have to see it. But be aware of it is kind of important. And so some of you'll develop some awareness about it from what we're doing here, in this set of videos. So you're saying probably, and I'm kind of pointing out with this, is if I instantiate a node in main, and inside a node, I create another node, and then that creates a node, and then in that node, another node's created, and then another node's created, I would say you're on the right track, because since this is a pointer, it can be a null data, it could be null, it can hold nothing. And it's not until we assign it a value that it actually does or completes that self-referencing. It's not until it's instantiated that it completes that self-referencing. So what we would have for this data inside of our constructor for node is we would have next equal to null or 0. I believe in Java it's null. Data is not instantiated yet. We can assign data to null as well. But that's where we're gonna store and we're gonna cast it to the object class. Basically, we're going to cast it to the very base class of the whole C# language. I'm probably doing it wrong here, and actually, you know what? Let's look at that. Because let's do that right. Java base class for all objects. I think it's just object. Oh, it's capital O. Okay. Same thing in C#. Okay, so what I'm saying is this object that's going to represent our data, it can be any data type. And if we can box it up to any data type that we want. And that's why this type of language works, is because of that dynamic binding capability. And everything we can treat as an object with polymorphism, so every object is it doesn't matter what kind of object it is. It could be an integer, string, a double, float. It could be a customer. It can be an employee object. It doesn't matter, because at the very base class of the Java language, we have the object class. So everything's an object. So if I want to create a node that stores information in Java, I just need to create, for that data, if I want it to be any kind of data type that I create myself, that I want to store in that node, I will use the object data type, because it's the very basis class. And therefore I can then, everything else will work with dynamic binding. And we have the goal of boxing the data and unboxing the data as part of the mechanism that allows us to do this. So more on that later. We're not gonna get too deep into it. But the idea is that we instantiate an object to hold data of any data type. Doesn't matter. And then we have some kind of reference to the next node in the list. Okay, so let's look at what we have right now on the whiteboard. And hopefully I don't get too scribbly. All right, so right now we look at our code and we see that I have this thing called a node defined, but in main I create a node. Well, what does the node have in it? Well, let's think about that. What is the node? Let's draw a little box for the node. Let's say that this is a node, a very scribbly node. And it's the node that we've called root. And at that node, since it is an address, it is a pointer, we can say, and I'm just making up these numbers, by the way, so you can see the mechanism behind the scenes. Let's say that this node is located at address 3000. That's where it exists in RAM. And that's automatically given to you when you instantiate it. But currently, it starts out at null, and it's not until we say new that we get that first byte that represents that node that we've declared. So in main, when we say node and root is equal to new node, that's what I've asked for. Is I've asked for a node, a memory, a block of memory that is size of node, and let's say that the size of node is 5 bytes. So that means from 3000 to 3005 on your RAM addresses, that's where this node exists. Oh wait, excuse me, 3004. Yeah, okay, let's throw that in there. And then that's where the node exists. Well, what does node hold? Well, the node holds some data. And it has a next pointer that points to the next node. Okay, well, what does that look like? Well, it looks like just like this. So it will go and it'll point to the next node. Now, let's get a little bit more verbose here, because I need to draw these boxes bigger. Yeah, much bigger. All right, so root is created. Root is created as a node. Here we go, nice big node, thank you. It has data that is an object. It could be any kind of object. It has its own address. This root node, when we said new, it returned to the root pointer, let's say address 3007. So root is a pointer that holds address 3007. So this is actually not root. Root, behind the scenes, is a pointer, and it has address 3007 in it, and it's said to point to this node. So that's actually what you're doing when you say equals new. You're taking a pointer that we've already declared and identified, because everything's a pointer, as root, and you're saying, hey, operating system, give me the memory for a node, and I'm going to store the first block or the first byte of that block of memory in my pointer called enroute. And it's going to reference that node. And we use enroute to reference it. And so enroute, it has its own address, but what it stores is the address of the data it points to that you create, that you ask for when you say new. Now inside of that is another pointer just like root. It's another pointer, but it's called next. And it is just like root. It has its own address. It is a pointer. It has its own address just like root. Root has its own address. We don't care about it. The one we do care about is what the address of what next is storing, which is going to be eventually another node that's going to have its own data, have its own next value, and this one, let's say that is at 4,000, and we're going to say that the next node is going to be equal to address 4,000. So 4,000 goes up here. And now those nodes are linked. And that's the self-referencing behavior. We get down to the end of the list and we put a 0 in here as null. That's null in Java. And that means we're at the end of the list. So there's a lot going on there. First, we're, Mr. B, you're talking about pointers. In Java, there are no, oh God, everything's a pointer. Okay, sorry. I went a little crazy there for a little bit. Apologize. This is how it works. Now, what's the behavior and kind of what's going on? Well, in this line of code, I've created the node, and now I can fill that node with some data. And I'm going to be very simplistic right now, and I'm going to put in really simple data. We're not going to do an object. I'm going to say I'm going to put in an integer called j, and I'm going to say j equals 1. And then I'm going to say, okay, Mr. enroute, your j, your data, equals j. Now it should be able to cast it down and box it up as an object there. I don't think I need to specifically say cast it down to an object, because j is an integer, but an integer inherits from object. So an object, j is an object, because it's the very base class. Object is the very base class of Java. So when I say enroute.data equals j, I'm just throwing an object in there that is an integer. And it could be a customer, it could be anything. As long as it's within this, infrastructure. Because everything's an object. And a pointer. So then I could say, okay, well, that's cool. I got my first item on my list. So let's do some printing. And let's just do this one. We're going to say j. It knows it's going to be an integer, so that should work out just fine. No, just j. No, why are you doing this? whatever. I don't know why it's doing that. Oh, I'm being silly. What do I want to print? I want to print the en routes data. And I may need to unbox that, because here we're going to say take the J, specifically make it an object. This is called boxing. We're boxing up J into the object. And then when I go here, I might want to unbox that as an integer before I print it. So you see how I'm using casting there to do the boxing and the unboxing. So I'm degraduating a variable down to object. I'm graduating a variable up to int. Yeah, because object is the base class. So it's actually a degraduation. But we call it boxing. And that's how you can store any data type you want with a pointer called next. And it's not until we say equals new that it becomes the actual data. Okay, what does this look like? Okay, well, let's get into it. Real simple. We're going to print out the data. Let's do a step into for this. Actually, let's do this. Why won't you let me set? There you go, or you better behave. I'm getting testy today. I need to quit that out. Well, yeah, of course I'm getting testy today because Java is going to be a stinker. Nor source root found for, okay, what is it you're complaining about? Oh, I probably got some silly things to fix up. Oh, yeah. Oh no, it's fine. It was working. I was getting a little temperamental there already, starting to have a conversation with Java. Okay, I'm going to rerun it, and then what we're going to do is we're going to do a step into. So we're at this line, and we want a new node. Step into. The first thing we do is we set next to null, meaning there is no next node. It does not store, next does not have any kind of value in it. Root doesn't have any value in it until new node is carried out. Then the new node is created and we assign the address of the new node to what root the pointer is storing. And then I can use root to reference the data that's inside of this node. And then just like root, next is the same thing as root. It can point to another node, and it's going to point to address 4000. I use next to reference that. But it's controlling this propagation of your next pointers and controlling it being set to null or to an actual memory from the asking or requesting for a new node using the new statement. And so right here we are just saying, okay, there's nothing yet there. Then we do the same thing for data. We're just doing some safety stuff, making sure that our pointers are nothing, and make sure that we control our new declarations so that we don't have an uncontrolled self-referencing behavior, because it would just perform an infinite loop. Because every time you have a node, and inside that node you have a next, and inside that next you have another next, and it keeps going. And so we're starting out with that default state. And then once that's done being created, we then assign the data equal to the value 1. So now I'm going to do is I'm going to say, okay, the data is an object, cast it to J. Now the data of this node that we've created holds the value 1. And then we output it. Very simple so far. We haven't gotten into the weeds yet. Yeah, we're heading there. We're heading there. All right, so this is kind of what I have. Let's just pretend that what I've written so far, we're next, when we've just started out like this, next points to 0. Because we just assigned it 0. It's not until we have not assigned, we've also assigned the data, but next is 0. So when I say 0, I'm talking about null, by the way. In fact, behind the scenes, it's 0. So we know that there's not another node because next is pointing to 0. We know that root's storing a node because it's filled with 3007, and we ran the new on it as well, and we can access the data and print the data. But this has been controlled because our first node, we always set next equal to null, and data equal to null. So then we put the number 1 here. Okay? Now, this is where we make it linked. And this is what I call the poor man's linked list. Let's say that we want another link. That means that we have now nroots data, nroots next. Right now, nroots next is null. It's not been declared yet. This has not happened with the next variable. We've done it for nroot. It's been declared yet, but this pointer is pointing to nothing. We have it, we've declared it, but it's 0. It's equal to null at this point. And that's where you get the control of the propagation. That's how you control the self-referencing behavior, so it doesn't run away from you in an uncontrolled loop. So what I would do then is I would say, okay, I want nroots next to be equal to a new node. Okay. And then I want to have nroots, since now nroot next exists, because we just said nroots next is equal to new node. What does that mean? Well, what have we done? Well, at this point, we've said nroots next equals to another node that we've got over here. And that new statement returns the address of a new node to this next variable, and it's going to store 4000 inside of it. Let's just pretend that 4000 is inside of there. And it links to this data. Sorry about my chicken scratches. It does, I'm left-handed. I'm sure some of you might be used to it by now, but we'll try to tailor it with plenty of explanation. So this next that we've just now instantiated asks for a new node. nroots next equals new node. So now nroots next has has a data object in it. So I can say nroots next dot data equals and let's just do a literal here, 2. We're just going to put 2 on there. I'm not going to create a variable for it. And now what we have is we've made this link. We've put 2 here. Root points to this one. And inside of this one, we reference ourself to address 4000 that points to this node. And this one's next points to 0. And we assign 2 for the data. Here we've got 1, the number 1 assigned. And those are linked. Whoop whoop, you guys got linked list down. You're done, we're done, you're good. Not quite, yeah, it gets a little, but this is it actually. No, quite, this is what a linked list is. It's this simple. It's the linked list manager that really gets complicated and how to automate this process of making links. So let's do another one. Okay, let's do this one. We're going to do one more, and then I'm going to talk to you about walking or traversing a linked list, and then we can move on into another video. So if I want another one, you guessed it. You might have been guessing it. What if I want another one? I just want one more. I just one more, please. Yeah. Guess what? That's what linked lists are for. I got you. I got you. So I need to go to nroots next. And what I'm doing is I want this next to be equal to a new node, to point to an actual address that exists, just like I had with this one. So I need to go to nroots next equals new node. So nroots next equals new node. And then nroots next dot data equals object 3. All right, well, what do we do? Okay, this line 29, what did it do? It said, okay, nroot, you're next. Oh, no, not nroot, but nroots next. It said, I want you to point to somewhere other than null. And remember, whenever we declare a node, the next defaults to null. So whenever we have this new node over here, that we say that new third node, oh my goodness, what happened there? Okay, my third node is going to get a little messy here. Something's going on there. That new node that we're having, its next starts out pointing to null. Starts out pointing to 0. That's its next. And because when we instantiate a new node, talking about this guy right here, when a node is instantiated, what do we do with next? We set it to null. So now I've set this next equal to a new node. Its next points to 0. And this one, let's say, has the address of 5000. Remember, I'm just making these up because this is all stuff that's handled behind the scenes by the operating system. It just gives you the data address to your pointer. So now this one's linked over to here. And then I add another piece of data. The next line that I have, I set the data to 3. Oh, that's a miserable 3. That's a better 3. That's a miserable 5,000. I mean, I'm just saying. Okay, so that's where the link is made. And then the next tier points to 0, null. So that means we're at the end of the linked list. And that's how we can tell that we've made it to the end of the linked list when we traverse it, because the way that we can visit every piece of data in our list, we have to crawl through every link to get to it. And that's where linked lists are brutally inefficient. Arrays are much more efficient at traversing than a linked list is. But a linked list is the only kind of memory format we can have where it's automated and you can just add one piece of data at a time versus have to manage copying over from, limited contiguous blocks of memory in your array. So to solve this horrible inefficiency, we use binary trees. It's just kind of the next natural evolution from linked lists. And, we're definitely not going to get into that. But we've built a linked list. It's built. So then let's look into a little bit on what sort of thing does the management class do? And because that's the next thing we're going to do. But let's first talk about walking and traversing this list. To traverse this list, what I would do is I would use a temporary node and assign it to each successive next node and print the data from each one. And I would do it for however many items were in the linked list. Well, I'm going to hard code it because I know that this has got 3. So I'm going to say for int I equals 0, I is less than 3. And usually what you would do is you would actually either traverse it with a while loop, because we wouldn't actually, you know what? That's the way we should do it. I'm going to say while, and another thing is I'm going to create a temporary node, temp. We're going to call it current. Okay? And I'm going to say while current does not equal null. And the reason why we want to traverse current instead of root is because if you use root and you say root is equal to nroot or nroot.next, you lose the head of your list, and you can't lose your head. So you always have to keep nroot pointing. So what we do is we traverse the list with a temporary pointer that we'll call current. So what is that going to look like? Well, okay, we're going to create, just like root is a pointer, we're going to create current. Current over here, current is just another pointer. It has its own address, and it's going to start out at 0, but what we're going to do is we're going to say current is equal to root. So when we say current is equal to root, we're saying go inside of root storage, get the address of the node, and assign it to the address that current is pointing to as well. And so they both reference the same memory now. And then I can use current to traverse the list because I'm going to lose my current position every time I go to the next position. Because I'm just using these pointers to traverse each memory location in RAM. So that's the next bit I'm going to do. I'm getting into weird spots here. Where am I at? Okay. I'm going to say current is equal to root, nroot. And that adds so that current now points somewhere that's not null. It points to address 3007. And we can then use this to traverse the list. And if I want to print out the data of each item in the list, here's how I would do it. I would say, okay, en route is preserved. We know where the head of our list is. It's always preserved there. So we always know where the address of the head of our list is. So we can always retraverse it. But while our current is not equal to null, I want to create an integer, and I'm just going to reuse this one. I'm going to say j equals, isn't that the one j equals currents data. And then of course we've got to unbox that. This is unboxing. We boxed it up in an object. Now we're going to unbox it back to an int. Then I can print that value that I grabbed and I unboxed. And that's going to print my first value that I put in, which is going to be 1. And then, the value 1 is printed. But then how do I get current to point to the next one over? Well, guess what holds address 400? What current is currently pointing to is address 3007, this guy right here. And its next holds address 4000, which happens to be in the next one in the list. So then what we say is we say current is equal to current's next. And when we say current is equal to current's next, what we're doing is we're saying current no longer points to there, current now points to there, and the address 4000 is in there. What does that look like in code? Well, we're going to do it in the while loop because we're using that to traverse. And I'm going to say simply here, current is equal to, oh, I need to do it in the loop because we're going to do it multiple times for every data item. Current is equal to current's next. And then the loop starts over again. I unbox J, since now current is pointing to the second item in the list, it is now storing address 4000. I can unbox the J that holds the value 2, the data of that particular node, and print it. And then the loop runs over again. Unbox the next link. Let's look at this in the debugger. Come on, silly. Do what you're supposed to. Oh, I screwed up. Oh, no, I didn't. We're good. Okay, so current is just starts out as nothing. We actually probably should assign it equal to null. But I immediately assign current to en route. And en route holds my data. And I can even look over here in the watcher. Let's just do this. This is kind of cool. Add this as a watch. Okay, now down here, we can actually scale into this and look at each one. So en route has a data piece, and then the data piece has 1, and then its next has a data piece, 2, and then its next has a data piece, 3. You see how it's kind of tunneling in just like recursion? So I'm just using this while loop to walk those .next values. So initially, the first data piece that en route is pointing to is 1, so we print the value 1. Then we say, okay, current is no longer pointing to that, and let's actually look at this. Current, we can see that current has 1. What we then say is current is equal to current's next. So that's when this happens. And now when we refer to current's data, we're referring to this current's data. So current is equal to current's next. If we look at current, we say its data is 1. As soon as this line runs, it's going to traverse forward. So then now current's data is 2. And we keep doing that until we hit to the very end of the list where current comes out as null, which breaks us out of the loop. So the next time through, then now we say current is equal to current's next again. Now this is going to hold address 5000. It's going to point over here, and we output that value unboxed. Then it does another one. It does another current is equal to current's next, and then current becomes 0, because that's what this next is holding, 0. There's no more links. We're at the end of the list. And that's why it's crucial to be setting your next to 0, because it's what you use, or null, it's what you use to control your self-referential behavior within a linked list. And so this is as simple as a way to break down your knowledge of a linked list and walk through it and kind of get an idea within the debugger of what's going on, what is happening behind the scenes here. Look into that unboxing behavior. We're going to be continuing on with this. We're not going to get too crazy into linked lists. I'm going to give you a little bit more into a linked list management in the next video, and we're going to do some simple linked list procedures as an example, and then we might get into the library part. We'll see. All right, guys. Have some fun with this. This one is fun. This is the best way to learn how to do linked lists. The best way to visualize it. The best way to see that it's a pointer, that it's pointing to, because everything's a reference type in Java and C#. All righty. Take care, guys. See you on the next one.